we welcome you here at the Technical Forum at the Group Exhibit Hydrogen and Fuel Cells 2013. You are invited to come in, have a seat, have a free drink, and listen to the next presentation and ask some questions at the end. Come on and enjoy here with us our next presentation dealing by the theme Portable LPG-Fueled Microtubular Fuel Cell by eZelleron, the CEO, Dr. Sascha Kühn. Give him some big hands, please.
Thank you very much for the nice introduction. Welcome to my presentation. Thanks for joining me. I talk about portable LPG-fueled microtubular fuel cells, and who doesn't know that? Power failures are very common, and we don't have enough electricity with us, so that's the topic we are dealing with. Portable power and mobile power applications are very good for e-bikes or flying objects or boats everywhere, in every market where you are away from the grid and you cannot recharge your devices. You need portable power. Compared to a lithium-ion battery, fuel cell systems are always lighter. On the y-axis the weight, and on the other axis the operating time. There's always a break-even point where portable fuel cell system is lighter than lithium-ion battery. If you look at different ways of energy storage, the best storage capacity has lithium-ion battery, which is the brown field over there. You can reach about 100 watt-hours per kilogram at a power density of 1000 watt per kilogram. But with a fuel cell system from eZelleron, you can improve that by a factor of 20. There's a lot of markets which we are interested in. These markets are on different power levels, and for example, for the 200 watt markets, which is the yellow bubbles, the size of the bubbles is the size of the market. And we fit them into this diagram. On the y-axis, the attractivity of the market, and on the x-axis, the risk to come into that market. And for the most markets, there are some small markets which have a very high attractivity and a low risk to go in. And these are attractive starting markets. On the other hand, together with a partner that has the possibility to take the risk for a bigger market, we can go faster into the bigger markets together with them. The values are based on a Pike research study from the year 2012. And to say some words more about eZelleron, our USPs are that we can use available fuels like LPG. You can see it in the first picture over there. Standard camping gas cartridges or lighter gas can be used instead of only hydrogen. And we have quick startable units for mobile applications. You can see such a quick start unit at our booth. So come to our booth B50 in hall 27 to see a 5-second quick start of the other microphone. Or?
Mit Ihrem Bart.
Aha, wenn ich weiter weggehe? Okay, sorry for that. it's you can come to our booth and see a solid oxide fuel cell start in about 5 seconds, which is quite impressive because there is no other supplier of solid oxide fuel cells that can start that quickly. Most of them need about 2 hours or several hours more. So we also built very extremely lightweight units due to our high power density. You will see at our booth also example for that in a flying object. And we are very cost efficient because we have already chosen very good powder suppliers, and we have the whole mass manufacturing in our hands, and mass manufacture the tubes already on big mass manufacturing machines. I come to that later. eZelleron was founded in the year 2007. We have 22 employees now, and we have several strategic partners like the Austria University and the Fraunhofer IKTS in Dresden. We are also located at the Fraunhofer site, the campus in Dresden, and we have a big IP portfolio of 13 worldwide patent families in US, Japan, and Europe. Several received strategic documents and a lot of publications. eZelleron got a pre-seed money of more than 10 million euros. Furthermore, we got seed capital of more than 3 million euros, and we have a founded project volume of more than 7.5 million euros. So we are quite well equipped, and we're able to do the development I show you now. The first part of my talk will focus on the anode substrate development of such a microtubular solid oxide fuel cell. The second part is focusing on the thin film technology, which is really the most necessary part of the technology to have a quick startable solid oxide fuel cell. And then I will show you some more aspects of the system design. Focusing on the anode, it is necessary to look for the polarization resistant and also to lower the activation energy and the reaction area, and to broaden the reaction area and to improve the electronic conductivity, which means you have to care about materials, temperature, particle size, distribution, and the microstructure. So the first thing you have to think about is how can I manufacture such an anode substrate? There is a lot of ceramic processing methods, and in our case we are looking for a very high number of units and high complexity of a workpiece. So that's the reason why here in the red square is the region where our parts have to be produced, and typically powder injection molding is the choice for such a product development. We have a very high requirements on the accuracy, and furthermore the price per piece is very important later on. So it's a perfect technology to manufacture such substrates, but as we realized, all in the world there is no binder systems and feedstocks available to make such a manufacturing. So we started to identify suitable combinations of organic adjuvants, wetting agents, dispersers, plasticifiers, binder systems, release agents and deformers. We did the whole mechanic, chemical, and thermomechanical process engineering for that, which was a lot of work. And with our binder and debindering technology, we developed a totally new system for powder injection molding, which has a lot of advantages compared to standard debindering technologies like thermal or catalytic binder systems. In our case, we use a solvent debindering, which is very quick and very low cost, and we don't have dangerous reactants or high polluting emissions during the process. So it's a green process and also very cheap. This is about our binder system. If someone is interested, we can talk about it later. The shear extruder is the first unit where the nano powders are compounded with. So it's important to learn about all the parameters needed for the later production, like gap width, temperatures, roller speed, and feeding speed. During the powder injection molding, there's again a lot of parameters you have to learn about, and afterwards you have the first parts which can be controlled, for example, by computer tomography, and you see that in the beginning there were still a lot of failures in our parts which could not be seen from outside but were inside of the tubes. And by different injection molding parameters, we were able to improve that and to get rid of any failures. The substrates have to be developed in many ways, not only the perfect structure, it's also the perfect microstructure, which is important because for hydrogen you need a medium, you need a usable pore volume which has to be above the medium free wavelength of hydrogen at operating temperature, and which means you have to come up with a substrate with very high porosity, but not too high, because you also have to include the electronic conductivity into the substrate. So the next step is how to manufacture the electrolyte, and there is a lot of things important for the electrolyte, mainly the internal ionic resistance and the oxygen vacancy formation enthalpy. And always you have to keep in mind that we want to build a system that has a very high power density, a robustness against thermoshocks, and a quick startability. And during that we want to overcome these issues. That means we have to care about all the materials, the temperatures, the thermomechanical stability of the whole system, and still we have to improve the ionic conductivity. This is only possible by using thin layers, because thin layers don't show the typical viable behavior. They behave like quasi-plastic films. It's more like a polymer film, the behavior, not like a typical ceramic unit, with the second advantage that the thinner the layer, the higher the conductivity and the lower the resistance. So that's what you have to focus for. The next thing is that for this thin layer you need a very low grain size to improve the mechanical stability. The conductivity of the layer also improves by that, and furthermore you need a good adhesion of that layer, because otherwise the layer will crack. This can only be done by nanopowders, very low sintering temperatures, so that means you need high green densities and impregnation processes. So we chose electrophoretic impregnation and electrophoretic deposition to manufacture those layers. You have to control the powder habitus. You have to correlate the layer thickness with the electric current during the electrophoretic deposition. So because we are heading for layers thinner than 10 microns, the deposition time has to be beyond 20 seconds, which means again it is possible to manufacture very cheap. And this shows you impregnated membrane. You can see that more than 180 microns deep we can come with the nanoparticles, so we get very good adhesion of the green layers with a high green density. And here you can see already that it's almost pore free, and the pores are always beyond wavelength of the light, so the layers are bright and shining and seem to be transparent. The resulting microstructure is that it's a microgranular microstructure, which means these layers have a very, very high thermoshock resistance and very good stability. Here you can see the whole microstructure again, starting with the tube on the left side. And in the last picture you can see that the layers are about 10 microns thick and almost free of any failures. We can mass manufacture these tubes. This shows the different steps of manufacturing again. And the advantage of these tubes is that they have a very, very high power density. They are not developed by scaling up processes, but we do a numbering up. And that means we have very quick development cycles. The long-term behavior is also quite good because we're heading for the mobile markets. 3,000 hours is the benchmark, and we have only a slight degradation in our 750 hours tests. Mass production of the microtubes is possible. I'll show you some pictures about the system development. This is, for example, a stack of our GoBot 125, which is a ring stack. The cells in the stack environment have lower energy densities, but still deliver more than 1 watt per tube, which is higher than any other microtubular developer can do. We have a very good fuel utilization. Thermocycling capability is excellent. Here you can see 1,000 cycles at a degradation rate of about 3%. In the stack environment, we have a higher degradation rate, but still in the limit that we need, and we can also thermocycle the whole stack at our automatic thermocycling test rigs. The next thing we have to do is to integrate the whole thing into a hot box. So there's a start burner inside, an afterburner, and a pre-reformer, and the whole gases come through connector plates into the inner side of the stack and go through the tubes and then to the afterburner. And we have a heat exchanger on the outside. So in a gas battery, this hot box is only one small part in the middle. There is isolation around it, and on the bottom you can see a gas cartridge, standard camping gas, and several valves, and we have a pump and buffer batteries included into the system. So we operate with LPG. This is our 200 watt stack. You can see that our booth, B50 here in this hall. The stack is at about 200 watt at typical values of 0.7 volts, 850 degrees C. And in the next step, we want to integrate several of these stacks into a bigger stack unit, which we need for a flying object that you also can see at our booth. So compared to other fuel cell technologies, we think that eZelleron's technology fits to all the advantages of a solid oxide fuel cell, like high efficiency, operation on hydrocarbons, not needed water management, and so on. And also has all the advantages of a PEM system, which means very high power densities above 0.3 kilowatt per kilogram, very good ruggedness against vibrations, and startup times below 1 minute, and more than 100 cycles, which you cannot do with a typical solid oxide fuel cell system. We have feedstocks available. Cells are mass manufactured and can be bought at our booth. We have stacks in small series productions and customer-made solutions of stacks. The hotbox customer-made solutions will be available in the end of this year. Gas batteries will be available from next year on, and also the customer-made solutions of gas batteries. And please come to us if you are interested in individual hybrid systems, because that's what we typically do together with customers. Thanks for your attention, and please cooperate with us. Thanks again.
Thanks a lot, Mr. Kühn, for this really interesting presentation here. So, are there any questions here in the audience right now? So, not yet. So, can you maybe say again, where's your booth? Oh, it's here at the Hydrogen and Fuel Cell exhibition.
Yeah, at the Hydrogen and Fuel Cell section, just straight here and then up to the front. Yeah.
Okay, so if there are any question comes...
Yeah, you can always come to our booth.
Yeah, or the week
I will be
until
there.
Friday.
I will be there.
Until Friday.
Until
Okay.
Friday.
Thank you very much. So, Mr. Kühn?
Thank you very much.
Thank you.